In this section, what we're going to do is we're going to take a look at how waves interact with one another. Now, you're going to get like an overview of the general ideas behind wave interactions. And I'm going to give examples of things where you have like ropes, but real wave interactions, we're talking about like radio waves, EM waves. So if you've ever been driving before, and you're driving and you're listening to the radio and suddenly either there's some static or you hear like another station kind of come in for a quick second, that's interference, that's what you're hearing. So we're going to talk about constructive and destructive interference in the second part, and that relates to something called superposition. And then we're going to talk about how a wave is reflected off of a boundary, and that's going to carry over to the lab tomorrow. And then we're going to look at what are called nodes and antinodes of a wave that's a standing wave, not a wave that's traveling. All right? We looked at waves that were traveling yesterday. We're going to look at a standing wave. All right. So we're going to define the two terms interference and superposition. So interference, imagine just two waves interacting with one another, okay, in some fashion or another. Whether it be constructive or destructive, we'll talk about in a moment, but just imagine two waves that interact. So imagine that you're at one end of a pool and another person is at the other end, and imagine the pool is perfectly still, the surface. If you hit the surface on your side, it's going to send a ripple out. If another person sends it or hits on their side, they're going to send a ripple. What happens when those ripples meet? What happens when two waves or wakes meet? What do you see sometimes? Yeah, so Ian says sometimes you see this. You see, like, if the two wakes meet together perfectly, you'll see something like this go on. Yeah. What else could you see?
Like bounce off.
You can see them bounce off each other, and you actually, what you'll see is you'll see them going past each other, but it looks like they bounce off. Yeah. What else? Instead of combining to become a bigger wave, you could also see little deficits or little dips. So when we look at constructive and destructive interference, it depends on whether or not the wave is like a positive amplitude wave or a negative amplitude wave. That will help us to differentiate between constructive and destructive interference. Now, superposition tells us that if we have two pulses, their amplitudes or displacements, right? The amplitudes or displacements can be added together when they coincide or when they meet with one another. So that was what Ian was just mentioning. If two little wakes from the water came together like this, you would see it kind of rise up and then come back down. You'd see that sum of the two waves. And that's what we're seeing with superposition here. That's what it says. So if you have two smaller waves that coincide, or two waves in general, they'll combine to make a third wave, an overall resultant wave. And we'll talk about how that works. So first, let's look at examples of these two topics. So constructive interference. Constructive interference would be, imagine two people were at the same, or at opposite ends rather, of the rope, and went like this and sent a positive pulse with the exact same motion, both on the top. You would have two waves coming toward each other. That's what you're seeing over here in part A. So you have a wave moving left to right, a wave moving right to left. One of them has a higher amplitude than the other. Well, when they come together, it's going to be like what Ian was mentioning, how the two waves combine. So then we go to part B. They start to come together, and you see like the outline of the original wave here, and the outline of this original one. But there's this kind of like weird intermediate stage where the two waves start to form one until they're actually coinciding, which is part C. And when these two waves coincide, if the height of this wave is, say, hypothetically 3 inches, and the height of this wave is 6 inches, the height of this wave would be 9 inches. Okay, so the sum of these two original waves here and here, which are these originals, come out to be one larger wave if they're both positive. Now, once they combine like this, afterward what happens is the big wave ends up over here now, like it passes through. The small wave passes through this way. So the waves literally pass through each other after they combine, and they come out on the other sides. So the big wave is now moving to the right, but on this side, the small wave is now moving to the left on this side. So they literally pass through one another. Okay, so you're going to see this. The waves come, the waves come, the waves come. They build up to one big wave, and then they pass through each other and continue going. Now, that's constructive. What's the difference? Just look at the diagram and tell me. What's destructive? What's the only real difference, eh?
That unlike constructive, where both are positive, this one destructive has one positive, one negative.
Yeah, so what would happen as a result?
Both of them would be diminished, or at least the positive one would become smaller.
Exactly right. So the idea of superposition tells us that we can add together these amplitudes. Well, if you have a positive amplitude, but you have a negative, they're going to partially cancel each other out. So for example, if the height of this wave, pick a number, a positive number. 5. The height of this wave, let's say, is 5. I'll put a dot up here. Well, this one will be less than 5, but something negative. So negative
3.
All right. Negative 3. So if we've got a height of 5 and then a depression of 3 or a height of negative 3, when those two waves come together, they're going to start to form together right here in part B. But look at part C now. 5 minus 3 just gives you 2. So the height of the resultant wave here would simply be 2. Because it's 5 plus negative 3, which is just 2. So superposition tells you that if you have two pulses passing each other, the height of the resultant is the sum of those two heights. The height of the result is the sum of those two heights. And then after they pass through each other, they come out on opposite sides again. This one had a positive 5. It still has a positive 5 afterward. This was a negative 3 moving left. It's still a negative 3. Now it's moving left, but on the other side over here. Did I talk about a bonus opportunity for you guys in here? All right, because the other class asked me yesterday. I meant to mention it, I forgot. Let me pause here and tell you about the bonus. So, for a little extra credit, 3 points worth. Okay, it's a higher extra credit value, but there's a lot of work to do. Here is your, well, here's the guideline of what I want you to do. I want you to either, well, it's up to you, you got to figure out how to do this, but either fix a string to something or leave it free. But what I want you to do is to be a pulse generator yourself. I want you to be like, like periodic waves that continue to repeat over and over. I want you to generate some sort of a pulse to get a standing wave. And I'll talk about the standing wave in a minute, but I want you to get that wave, that look that we've seen before, like the transverse wave has. And I want you to record yourself doing it. Now, while you're recording it though, you need to put like a tape measure behind it, or a meter stick of some sort. So that afterward, when you're done recording the video, you can freeze the video and measure the wavelength and the amplitude of the wave you created, but in real dimensions. So if I'm, say hypothetically, I take a rope, and I'm sitting here going like this with the rope, all right, and I did this like curved nature with the rope. I want to do it for a while until I get it to be pretty consistent the way it is. Then, so you're recording this while it's happening. Then you take a screenshot or a freeze frame or whatever you call it of that instant in time when the rope makes a nice curve. Okay, then using that curve, I want you to measure the wavelength and I want you to measure the amplitude of that actual wave, those parameters that we talked about the other day. But to do that, you can't just do it on the screen. You need to have a tape measure behind it so you can line up the tape measure so that you can see, like, say that first crest is at 7 centimeters and the second crest is at 35 centimeters. You can just subtract the two and figure out the wavelength. All right, so you're going to have to figure out how to do this, but it's a little more work than the last few. If you'd like to do it, obviously. I'm not going to make it due until Monday. I'll give you the weekend. So if you want to have it for this test, you want to do it over the weekend, you can do it then. All right. Before I get into this, let me tell you is when we have a free boundary or a loose boundary, the incident pulse and the reflected pulse are the same thing. Okay, you send an incident pulse, the reflected pulse comes back with the same exact amplitude. Right, the same height. This is assuming there's no friction, obviously. If there was friction, some of that energy would be lost, and you saw that in the demonstration there with that applet. Again, this incident pulse hits the end. The tension in the rope causes it to pull back down and send a reflected pulse on the opposite side. Okay, on the opposite side. Yeah, sorry.
Why does it matter if it's, wait, so free means that there would be somebody like on the other end of it pushing it back, or would it just be a pull? Like, I don't know what's supposed to be a pull or like a...
Alright, so in engineering and vibration analysis, you look at the end fixtures. So they're called boundary conditions. And if an end is fixed where it's not able to move versus an end where if it's sliding down, it behaves differently. So, for example, systems in general, you have vibrations that occur. Well, look at a guitar. How are the end of guitars fixed? They're fixed like this, right? The actual guitar is actually, the string is stuck on you. The string is not tied around something where it can oscillate up and down. So based on these end fixtures, the waves behave differently. So these are just two of the simplest ones that we're going to look at. Again, this is really an overview. A lot of the material for waves and interference comes about with like electrical engineering. Okay, that's what you can see a lot. I just want to give you guys a heads up, more of like just the gist of this, what you should know. Not mathematical, we're going to do, it's all conceptual for this section. There's no mathematical portion. Okay, so again, the idea is the boundaries are what affect the wave that comes back from the fixed boundary. So let's go back to this term standing wave that we keep talking about. And I'm going to pause the video because I want to show you in the computer what a standing wave would look like. Here, the easiest one to look at before we even go into our definitions is right here. It's like a guitar string. If you were to pluck a guitar string, it's fixed on both ends. It would vibrate up and down like this. This is the same string in 5 instances. This is not 5 different strings. Again, this is, take a guitar string. Here's the guitar string normally. Flat, horizontal, right here, right? You pull up on the guitar string, or you pluck it, then what's going to happen? It's going to vibrate up and down. Now, imagine though, if you had a fixture in the middle of that string. There's I forget the term. Anybody play guitar here? There's something that you can put on the guitar to change the pitch or the octave. What is it? Capo, that's it. Somebody said the other class it was another word. I'm like, I don't think that's it. That's something else. But that is it. You put it and it changes the. Is it to go up to the next octave?
Yeah.
Okay. So usually this tool is used on a guitar, so it changes the length of the chord, which changes the frequency, which goes up to the next octave. But imagine if you had a guitar string that somehow was fixed in the middle, right smack in the middle, and you're able to pluck both sides of the guitar string. You plucked one down and one up, and you let go. That's what this would look like here, right? Think about these ends right here as the end of a guitar string here and here, and you fix the middle of the guitar string. You take the guitar string and pull this one up, you take this one and pull it down, or the same, both up, it doesn't really matter, but then you let go at the same time. This would start to do this, and this half would do this. And continuously, if you have more of these fixed points, you have more of these oscillations. So I wanted to discuss that so you can understand these definitions a little bit better. So a standing wave is created when there are 2 or more, really, in this case 2 we're looking at, waves of the same frequency, wavelength, and amplitude. If you recall from yesterday, Victoria helped me out with this. And when I was doing, remember we were like sending pulses? And there was one point in time where the wave was kind of just like oscillating on the slinky. Let's try and, well, let's see if we can maybe show it real quick so you have an idea what this looks like a little bit better. What was your name? So, there was a point in time where yesterday, like we could send like a simple pulse, you know? There was a point in time where if you had the right frequency, and we got it at one point where you had like a standing wave. And once you like get it down, there we go, good. Okay, do you see the middle is not moving? The reason being, did you start moving your hand at the same time too? Okay, if we look, we can see that it's kind of rotating at the same time. We want the middle right here to not be moving. It's really not. You notice that? And you see this end moving up and down, and you see this end moving up and down. What that is this right here. Okay, this is the middle that's fixed. These were the ends. This was me and Kevin holding it, and this was the pieces going up and down on each side. So a standing wave is really caused when 2 waves combine that have the same frequency, amplitude, wavelength, all those characteristics in common. The result is a standing wave. This is a huge topic if you're going to ever study like sound engineering or acoustics. Okay, that's where it's really important. You're not going to see much of it in like mechanics of physics, but more in vibrations and sound. But what you get as a result are these things called nodes. So here, or here, all these locations where it's fixed, I keep calling them fixed points, it's a node. And a node is where you have destructive interference. Okay, you have complete destructive interference. The 2 waves that are passing each other cancel out right in that location. So you get no resultant wave there. And as, no pun intended, but as a result, you get nothing there. Okay, there's no wave at all. This is destructive interference. These are constructive interference. So these 2 waves are coming together, they're standing waves, and they're meeting, and they're canceling each other out right here. But it continues over and over and over again. Now, the opposite of a node is an antinode. An antinode is a point that's halfway between the nodes, where the largest amplitude occurs. So, right here, and right here, you have antinodes. Right here, you have an antinode. In this third one down, you have 1, 2, 3 antinodes. So the antinodes are like, if you took a vertical line and connected the min and the max, that's an antinode right there. That's another one. That's another one for this wave. For this piece down here, you have 3 antinodes. For this one, you have 4 antinodes. So what do you notice if you pick up on like a pattern here? For the first one, you had 2 nodes and 1 antinode. Kira?
2 nodes are all 7 nodes.
2 what?
There are 2 nodes and there's 1 antinode.
Be careful. Go to the second one though. Now you have 3.
Yes, there's 1 less.
1 less. That's better. Because if you say there's 2 for 1, it would be like 4, 2, 6, 3. Yeah. So there's always 1 less. So the number of nodes is equal to the number of antinodes plus 1. Okay, that's the relationship that you'll always see. You're going to have these fixed points for a standing wave. If you have 5 nodes or fixed points, you have 1, 2, 3, 4 locations where antinodes exist. Okay, so antinodes are the locations where you have constructive interference and you have a maximum amplitude of the standing wave. Now, if you were to look at what Kevin and I had just shown with the slinky, and you were to look at it on your, well, do we have time? Let's do it. Let's do it actually. All right. I need a volunteer to help record on my iPad. So let's take a vertical line right here. Okay, it doesn't matter where, just pick a random spot right here. Okay? Now, along that vertical line, see where it intersects the waves. The green wave, it's not very vertical this line, but I'm trying my best. The green wave, its height right here would be about 10, I'd say. The height right here, that's the green wave up top right there. The red wave, I'd say its height might be like 7. And then the blue wave over here might be like -4, around that area. I'm not going to make it work perfectly. So just look at your numbers. Look at your numbers. If the green and the red wave had been the original waves, right? You'd have 2 positive waves, 1, 10, 1, 7. What would that add up to?
17.
But then we get 17 for the third wave? No, the third wave is -4. So there's no way that these are the original waves, which means there's no way that this is the resultant wave. So you can rule that out. The blue is definitely not resultant. Then you can go ahead and you can look, you can say, all right, well, let's look at the other option. Let's say that these were the original waves. Here. 7 as a positive, -4 as a positive, 4 as a negative. Sum these together, you would get what? 3. But the last wave is 10. So clearly, these are not the original waves, which tells us that the green one is not the resultant. So blue is not the resultant, green is not the resultant, red is definitely the resultant. But let's prove that that's true. Again, the numbers are not right, I did that on purpose. 10 and -4 would give you 6. And we're seeing the height of this wave, I picked arbitrary numbers, but would be the answer to the sum of those two. So if you were really doing this with a grid in the back, it would work out perfectly. I was picking heights. So in reality, yes, this would really not be -4, but this would be -3. Okay, that's what that exact value would be if those 10 and 7 numbers were correct. But 10 and 7 were just arbitrary numbers I chose. If the idea here is that at any instant along the waves, the sum of 2 of the waves should equal the third. If that doesn't happen, if that doesn't hold true, it can't be the resultant wave. So for example, in this example, as Kira noted, the resultant wave is generally between the other 2 waves. But don't let that confuse you. Say this is the first wave. This is the second wave. They're both positive waves, aren't they? So where's the third resultant wave definitely going to be? Somewhere above it. Somewhere up here. I have no idea where. Okay, but I'm just drawing arbitrarily here. But if they're both positives, the sum of 2 positive waves is constructive interference, making a third and larger resultant wave using superposition. So you can't assume it's in between, but it will be if there's 2 waves on top and bottom there. Okay, one above the axis and one below.